All right, so finishing off this lesson, then we just talked about comparing intensity. Sound is measured with a decibel system, and it works in magnitudes of millions for each range. So to make the numbers manageable, and also to force them to result in a linear relationship, physicists use logarithms to analyze sound intensity. So now I understand you won't learn about logs till grade 12, so I'm going to get rid of the logs for you, and we'll work with it in a different format. So the first equation here, B, so I'll put over here a legend here, where B is bells, so it's just a unit of measure for sound. Okay, I1 and I2 are intensities. All right, and I1 is usually the original intensity. So there's your kind of your legend. Okay, so solving for I1, I'm going to get rid of the logarithm so you don't have to deal with it. So just to show you part of the calculation, divide both sides by 10. So we have bells divided by 10 equals log of I1. What that turns into B then is the first intensity is equal to 10 to the exponent bells divided by 10, or B divided by 10. So you put that formula. It has no logarithms, just using your exponent button on the calculator. Should be no problem. The other one, divide both sides by 10. And I got to add, I guess, to the legend what dB is. Sorry about that. I thought I got it all. So dB is just the change in bells. All right, so how much it's changed. Most of you probably already had assumed that. So log of I1 over I2. So a comparison of intensities, I1 over I2 equals 10 to the exponent, change in bells divided by 10. That's your second formula. Now the one thing I do want you to remember, or maybe emphasize here, is on the previous page we came up with a comparison of intensity as well. So I1 over I2 equals, so we just calculated it to be 10 delta B over 10. But that's also equal to the intensity that we found or discovered down here. So R2 squared over R1 squared. So please keep that in mind. Actually, I would prefer you to write it like this on your cheat sheet, because when you run into a question that requires you to combine those concepts, you have it readily available. You already know that those are all equal to each other. So some examples. So given a sound source's intensity is 5 times 10 to the negative 6 watts per meter squared, determine the intensity if. So the distance from the source is doubled. So right away, we're talking about intensity, and we are talking about doubling the distance. So we want to determine the new intensity. So I1 over I2 will equal, if our distance is doubled, so R2 squared over R1 squared. So what's going to happen here, I1 is 5 times 10 to the negative 6 over I2. Distance source is doubled, so let's change R2 into 2 times R1. All right. So cleaning that up a little bit here, I'm going to leave this side for a second over I2. On the top, 2R1 squared will become 4R1 squared over R1 squared. R1 squared will cancel out. And what we would find is that 5 times 10 to the negative 6 over I2 is going to equal 4. We're rearranging it. I2 is equal to 5 times 10 to the negative 6 divided by 4 watts per meter squared. So if you double your distance, so let's say you were at the speakers at a concert, you go twice as far away, therefore you would quarter your intensity. All right, so if you were 10 meters away, and you move to 20 meters away, it'll be 1/4 as intense. Okay? So B part, what happens if you get closer? What happens if you move 1/4 of the distance? So let's say you're at 16 meters away and you go down to 4. What happens? Same process here. Some of you are probably already anticipating what's going to happen. So 5 times 10 to the negative 6 over I2. So this now becomes 1/4 R1 squared over R1 squared. So I can skip a step here. R1 will cancel. And 5 times 10 to the negative 6 over I2 is now going to equal 1/4 squared is a 16th. So I2 equals 16 times 5 times 10 to the negative 6 watts per meter squared. You can calculate it. I just like keeping it separate so you can see if you move from 16 meters to 4 meters, the intensity is 16 times greater. The intensity is 16 times greater. All right. So it's an inversely squared relationship. Okay, next example. How many times more intense is a motorcycle, 100 decibels, than a passing train of 70 decibels? Okay, so how many times more intense? Well, we know the change in decibels is 100 minus 70. Don't know why I use brackets there. So 30 decibels. How many more times intense? So I1 over I2 equals 10. So the exponent dB over 10. So 10 to the exponent 30 over 10, which is 10 cubed. And there's no units here because I1 over I2, it's a comparison. So therefore, the motorcycle is 10 cubed times louder or more intense. So 1,000 times more intense on your ears if the motorcycle goes by compared to the train. All right. One last example then. Passing train produces sound at 70 decibels, measured 3 meters away. How far do you have to stand so that the decibel level is 50? So we have a change in decibels. So we got to take that into account. So 70 minus 50 is 20 decibels. We're going to be using this relationship right here, equals, and we got a change in distance. All right. So now we have to be careful here because the decibel level is a decrease. All right. Because the intensity is a decrease, we're going to have to use negative 20 here. All right, because it's a decrease in intensity. Okay, now you're going to figure this out because if the number comes out backwards, you know you used the wrong positive or negative number. So R2 squared equals, and over 3 squared. So you get 10 to the exponent negative 2 multiplied by 3 squared equals R2 squared. All right, so 10 to the negative 2 is 1 over 100, okay, or 0.01 times 9 equals R2 squared. And that's going to end up being closer. So I did do it backwards. I should have left it as a positive, right? Because the decrease, that would be my mistake. Yeah, the formula was fine the way it was. So, my mistake, I apologize. That intensity, because there's a decrease in it, we're looking at the positive change here. So it ends up being 100 times 9, so 900. And we have to take the square root of the 900 then, which gives you 30 meters. So therefore, must move back to 30 meters. All right, so there we are. So you move back to 30 meters if you want to go from 70 to 50 decibels. You got to move back a significant distance. You got to move back 10 times farther than you're already standing. So it is a significant change. The last component here that I'm looking at then is the Doppler effect. So the Doppler effect, it's a physical phenomenon that everyone has experienced at one point or another. This is that change in pitch or frequency. So it goes from high pitch to low pitch. So as a train approaches blowing the whistle, you can hear that change in pitch. Or if a car is honking its horn when it approaches you, it sounds like a high frequency, then it goes to a low frequency. And that's just because of your location relative to the waves. So I would recommend at this point watching the short little video that I have down below in applets and videos or applied videos before watching the final segment of this particular lesson, just to give you a feel, and then I'll finish up the math. So I'm going to cut the video off here because it's a good time for you to stop and go and watch the video that I've attached. It won't take you very long, and then we can come back and I'll show you the calculations of the math involved.